Hello everyone, welcome to my presentation. I'm the student of Sri Venkateswara College of Engineering, Bangalore. My name is Srushti S. from the Department of Computer Science and Engineering. The subject is mathematics. Now I'm going to discuss few concepts regarding vector line integration. Let's go with the introduction to vector line integration. Vector line integration is a mathematical concept used to calculate the work done by the vector field along a curve. It is an important tool in physics and engineering to analyze the systems with changing forces or fields. By integrating the dot product of the vector field and infinitesimal displacement along the curve, we can find the total work done. Vector line integration is represented by the line integral symbol, and it is extension of regular integration to multiple dimensions. Line integrals and parametrization. Line integrals are calculated by the integrating a scalar or vector function along a curve. Parametrization is the process of representing a curve as a function of a single variable. The parametric equations x equals f of t and y equals g of t are commonly used to represent the curves in two-dimensional space. Vector fields and assign a vector to each point in space representing the physical quantity such as force or velocity. Vector line integrals are used to calculate the work done by a vector field along a curve. The line integral of a vector field f along a curve C is denoted as integration f into ds, where ds is the infinitesimal displacement vector. Evaluating vector line integrals. To evaluate a vector line integral, we must first parameterize the curve C. Next, we substitute the parameterized equations into a vector field f to obtain a f of t. Then we calculate the dot product of f of t and the derivative of the parameterization and integrate the result over a curve. Types of vector line integrals. There are two types of vector line integrals, path dependent and path independent. Path dependent integrals depend upon the specific path taken between 2 points. Path independent integrals are also known as conservative integrals, only depend on the endpoints or insensitive to the path taken. Line integrals in two dimensions. In two dimensions, a line integral calculates the work done by the vector field along a curve in the xy plane. It is calculated by integrating the dot product of the vector field and the tangent of the curve over a curve's parametrization. Line integrals in two dimensions can also be evaluated using either the parametric form or the path independent form, depending upon the circumstances. Line integrals in three dimensions. In three dimensions, a line integral calculates the work done by a vector field along a curve in space. The line integral is computed similarly to the two-dimensional case, but with the additional component for a z coordinate. It is important to choose an appropriate parameterization for the curve to ensure the accurate calculations. Green's theorem. Green's theorem relates a line integral around a simple closed curve to a double integral over the regional enclosed by the curve. It states that the line integral of the vector field around a curve is equal to the double integral of the curl of the vector field over a region. Green's theorem is powerful tool that simplifies the calculation of the line integrals in a certain cases. Stokes theorem. Stokes theorem relates the line integral around a closed curve to a surface integral over a surface bounded by the curve. It states that the line integral of the vector field around a closed curve is equal to the surface integral of the curve of the vector field over a surface. Stokes theorem is the generalization of Green's theorem of three dimensions, and it is useful for calculating the line integrals in more complex scenarios. Example of a vector line integration. Example 1, computing the work done by the force field along a straight line segment. Example 2, evaluating the circulation of the magnetic field around a closed loop. Example 3, calculating the flux of a vector field through a closed surface. Applications of the vector line integration. Vector line integration is widely used in physics, engineering, and applied mathematics. It is used to determine the circulation of a magnetic field in a electromagnetism. It is the crucial for calculating work, circulation, flux, potential energies, and other physical quantities. Applications includes fluid dynamics, electromagnetism, mechanics, and optimization problems. Limitations and challenges. Vector line integration may become a complex when dealing with highly curved or irregular curves. Some vector fields may not be conservative, making the line integral path dependent. Accurate parameterization of curves and choosing appropriate paths are essential for the obtaining of meaningful results. Let's end up this vector line integration with a conclusion. Vector line integration is the powerful mathematical tool for analyzing the vector fields along the curves. It allows us to calculate the work, circulation, flux, and potential energies in various fields. Understanding the principles and applications of a vector line integration is crucial for solving a real world problems. Thank you.